A coordination complex is the product of a Lewis acid-base reaction, in which a central metal atom or ion forms coordinate covalent bonds with neutral molecules or anions called ligands. Similar to the terms central metal and ligand, there are some other terms like coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic complex, and heteroleptic complex, which are used with reference to coordinate compounds. Hence, you must get familiarized with these terms to understand different aspects of coordination chemistry. So let's go through these terms in detail. The first term is central metal atom or ion. The atom or ion to which one or more neutral molecules or anions are attached in a definite geometrical arrangement around it is called the central atom or ion. For example, the central metal ion in NiNH3 6+2 is Ni plus 2, in FeCN6 -3 is Fe plus 3, and in COCl6 -3 it is the Co plus 3 ion. As the central metal atom or ion acts as an electron pair acceptor, it is also referred to as a Lewis acid. Another important term is ligand. A ligand is any atom, ion, or molecule capable of donating a pair of electrons to the central atom. A ligand is also known as a coordination group. As ligands are electron pair donors, they act as Lewis bases. Ligands may be simple ions such as halide ions, small molecules such as water or ammonia, or large molecules such as ethane 1,2-diamine or ethylene diamine tetraacetate ion. The number of atoms in a ligand that bind to the central atom in a complex is referred to as denticity. When a ligand is bound to a metal ion through a single donor atom, as with a chloride ion, a water molecule, or an ammonia molecule, the ligand is said to be unidentate. Ligands that contain two donor atoms are known as bidentate or didentate. Common examples of didentate ligands are ethane 1,2-diamine, dimethyl glyoxime, and oxalate ion. As you can see, these ligands have two donor atoms that can simultaneously bind to the central metal atom. Ligands with several donor atoms are called polydentate or multidentate ligands. A classic example of polydentate ligand is the hexadentate ligand, ethylene diamine tetraacetate ion, EDTA. You can see from its structure that it binds to the central metal ion through 2 nitrogen and 4 oxygen atoms. Ligands like ethylene diamine and EDTA, which have lone pairs of electrons on more than one atom, are capable of binding to the central metal atom or ion through more than one coordinate covalent bond. Such ligands are called chelating ligands. Some ligands have two different types of potential donor atoms. but use only one of them to form a coordinate covalent bond with the metal ion. Such ligands are called ambidentate ligands. The NO2- ion is one such ambidentate ligand capable of coordinating to the metal atom or ion through the nitrogen or oxygen atom. Similarly, the SCN- ion can coordinate through the sulfur or nitrogen atom. Now, let's look at another important term: coordination number. The total number of ligand donor atoms to which the metal is directly bonded is known as the coordination number of that ion. For example, the coordination number of silver in the complex ion AgNH32+ is 2, while that of nickel in the NiNH3 4+2 ion is 4. Similarly, the coordination number of copper in CuEn2+2, a complex with a didentate ligand, is 4, while that of cobalt in COC2O4 3-3, another complex with a didentate ligand, is 6. Coordination entity or coordination sphere is a common term we use with reference to complexes. The central metal atom and the ligands attached to it are collectively termed as the coordination sphere or coordination entity. For example, in the complex K4FeCN6, Fe, along with the 6 cyanide ligands, is the coordination sphere. The coordination sphere is written inside square brackets, while the ionizable groups are written outside the bracket and are called counterions. For example, in the complex K2NiCl4, the coordination sphere is NiCl4-2, and the counterion is potassium. Coordination polyhedron is another term we use in coordination chemistry. In a coordination sphere or entity, the ligands are attached to the central metal ion in such a way that it gives a definite geometry to the complex. Thus, in a coordination entity, the solid figure defined by the position of the ligand atoms directly attached to the central atom or ion is known as the coordination polyhedron. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH3 6+3 is octahedral. NiCO4 is tetrahedral, while PtCl4-2 is square planar. One of the most important terms we often use is oxidation number of the central atom. The oxidation number of the central metal atom in a complex is defined as the electric charge it would carry if all the ligands were removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses after the name of the central metal atom. For example, the oxidation number of iron in FeCN6-3 is +3, and it is written as Fe3. Let us learn the method to determine the oxidation number of the central metal atom in a complex. Let's take K4FeCN6 as an example. As the complex has 4 monovalent cations outside the coordination sphere, the complex ion carries a charge of -4. That is, FeCN6-4. Let's assume the oxidation number of the central metal atom as X. The cyanide ion is a monodentate negative ion. Knowing that the complex carries a charge of -4 and has 6 monodentate negative ions, the oxidation number of iron can be determined as X plus 6 multiplied by -1, which is equal to -4. On simplification, we get X is equal to +2. Thus, the oxidation state of iron in the given complex is +2. Here is a simple problem for you. Calculate the oxidation number of the metal atoms in the complexes given here. In the first case, there are 3 cations outside the coordination sphere. Hence, the charge on the complex ion is -3. The oxalate ion is a bidentate ligand. Each oxalate ion carries a charge of -2. The oxidation number of iron, which is assumed as X, is calculated as X plus 3 multiplied by -2, which is equal to -3. On simplification, we get X is equal to +3. Hence, the oxidation number of iron is +3. Similarly, the oxidation number of copper and silver in the other 2 complexes are calculated as +2 and +1, as shown. Finally, let's look at the terms homoleptic complex and heteroleptic complex. A complex in which a metal is bound to only one type of ligand atoms is known as a homoleptic complex. For example, CONH3 plus 3 and FeCN6 minus 3. On the other hand, a complex in which a metal is bound to more than one kind of ligand atoms is called a heteroleptic complex. For example, CONH3 4ClBr plus 1 and CrNH3 4Cl2 plus 1